Hi everybody, and welcome to our module on pressure volume loops. Shown on the left side of the screen are the changes in left ventricular volume and left ventricular pressure over time during the cardiac cycle. The left ventricular volume curve is on the bottom, this is shown right here, and the pressure curve is on the top, shown right here. And these two curves are both elements of Wigger's diagram, which I talk about in the video on Wigger's diagram. Now if you took the volume at each point in time and the pressure at each point in time, and you plotted the volume along the x-axis and the pressure along the y-axis, you would get a square shape like what I've shown on the right side of the screen. And this is called a pressure volume loop. It shows you the changes in the left ventricle during one cardiac cycle. There's no time in a pressure volume loop, so you just have to know that as the cardiac cycle moves forward in time, the pressure volume loop will move in a counterclockwise manner like this, around and around. So what we're going to talk about in this video are all the different things that you can read off of a pressure volume loop and how it changes in various cardiac conditions. The first thing I want to point out is that there is this short portion of the left ventricular volume versus time curve that is flat, meaning that volume is not changing. At the same time, the pressure in the left ventricle is rising, so anytime the volume is not changing, that's called isovolumic, and the reason that the pressure is rising is because the left ventricle is contracting. So this portion here between the two green lines represents isovolumic contraction, and that is denoted on the pressure volume loop by this green line here on the right side. The volume is constant, so it's a straight line, but the pressure is rising, so we're moving up the pressure on the y-axis. And the reason the volume is not changing is because at this portion of the pressure volume loop, both the mitral and aortic valves are closed, so no blood can get in or out of the ventricle, therefore volume cannot change. There's also a point on the volume versus time curve where the volume is flat, but the pressure is falling. This is isovolumic relaxation. It's denoted by the red line on the right side of the screen. What's happening here is that once again the mitral and aortic valves are closed, so no blood can enter or leave the ventricular chamber, but the pressure is falling because the myocardium is relaxing. You may have noticed this curved line at the bottom right of the pressure volume loop and this straight line at the top left. Let's talk about what those lines mean now. So this point right here is the end of systole. We'll talk more about that in a minute. And this point down here is the end of diastole. So let's talk about the end of systole first. This is the end of systole where the ventricle has finished contracting and ejecting blood. The mitral and aortic valves are closed, so there is a closed chamber of the ventricle that no blood can get in or leave. I want you to imagine now that if we stuck a needle into the left ventricle and we injected just a little bit of blood at this point in time at the end of systole, that would slightly increase the pressure and volume in the left ventricle to a point that's, let's say, right here. If we once again injected some blood, we'd get another point right here. And if we do this same thought experiment and imagine removing a little bit of blood at the end of systole when all the valves are closed, we would lower the pressure and volume to a little point like down here, and we could remove some more blood and we'd get another point down here. So from this thought experiment, you can see that the addition of a little bit of volume at the end of systole or the removal of a little bit of volume creates a series of points, and that makes a line, and that line is called the end systolic pressure-volume relationship. And that line is determined by characteristics of the myocardium, and we'll talk later about some things that can change that line. We could do the same thought experiment here at the end of diastole. If we add a little bit of blood to the ventricle when all the valves are closed and it's a sealed chamber, we would create another point here. And if we added some more, we'd create another point here, and we could remove some blood and create a few points down here. And then we would get a curve that looks like what I've drawn on the screen, and that's called the end diastolic pressure-volume relationship. And that also is determined by characteristics of the ventricle, and we'll talk about things that can change the end diastolic pressure-volume relationship later in this video. Now what I want to do is go through the pressure-volume loop and point out where the mitral and aortic valves open and close. So I told you before that this flat portion of the left ventricular volume versus time curve represents isovolumic contraction. In order for isovolumic contraction to occur, the aortic and mitral valves must be closed. Therefore, at the beginning of isovolumic contraction, that is when the mitral valve closes. And I've denoted that on the left, and I've also denoted it on the right on the pressure volume loop. We now enter the period of isovolumic contraction where the pressure in the ventricle rises. At some point, the pressure gets so high that the aortic valve opens, and that's what occurs right here on the left. You know the aortic valve is opening because this is the beginning of the point where volume falls in the left ventricle. That means blood must be leaving, and therefore the aortic valve must be opened. And I've pointed where the aortic valve opens on the pressure volume loop as well. Now at some point all the blood that is going to leave the left ventricle has left, and we now enter this section down here, which I told you was isovolumic relaxation. So at the beginning of that section the aortic valve must close, and that's what happens here on the left side of the screen, and I've pointed it out at the right side of the screen as well. And I told you before that this is the end of systole, so naturally that's where the aortic valve closes, at the end of systole. Then we go through that brief period on the left where we have isovolumic relaxation, and then the mitral valve opens, and that's shown now on the left side of the screen and also on the right. So it's important you know which points in the pressure volume loop represent the opening and closing of the aortic mitral valve, and now we've gone through all of those in this slide. I want to also point out that when the mitral valve closes, that is one component of the first heart sound, S1, and when the aortic valve closes, that is a component of S2, so therefore you can identify S1 and S2 on a pressure volume loop from knowing where the valves close. And on this slide I've pointed out where systole and diastole are found on the pressure volume loop. I told you before that this is the end of diastole when the left ventricle begins to contract. This is isovolumic contraction here. This is when blood is being ejected from the left ventricle here, but everything shown in red on this drawing represents systole. Right here we have the aortic valve close, and then we have isovolumic relaxation, followed by left ventricular filling from the left atrium, and that all represents diastole. And if you appreciate that, it's easy to identify some of the important volumes and pressures inside the left ventricle. This point here is the end of diastole, therefore the corresponding point on the x-axis is the end diastolic volume. The corresponding point on the y-axis is the end diastolic pressure. This point here that I'm circling with my pen is the end of systole, so therefore the corresponding volume at the end of systole is obviously the end systolic volume. And now we can identify even some more important parameters of the left ventricle. So the difference between the end systolic volume here and the end diastolic volume here is the stroke volume. This is the volume of blood ejected from the left ventricle with each heartbeat. The wider the pressure volume loop, the more volume that the heart is pumping. This point down here at the bottom is the volume at the end of diastole. That's the amount of filling of the left ventricle, and that represents the preload of the heart. This point up here is the point at which the aortic valve opens. That represents the afterload. In other words, the left ventricle has to raise the pressure up to a point such that it can open the aortic valve. The more afterload, the higher the pressure will have to become in order for the aortic valve to open. So the afterload is always found here in the top right corner of the pressure volume loop. For the next few slides, I'll go through how the pressure volume loop changes when various important left ventricular parameters are modified. So for example, we'll go through what happens to the PV loop when there's a change in preload, afterload, contractility, or compliance. Now in reality, all of these parameters are interrelated. You cannot change one without affecting the others. For example, if you've watched the video on Starling curves, you know that when the preload goes up, the contractility goes up via the Frank-Starling mechanism. So all of these parameters are interrelated, but what we're going to do in the next few slides is consider the artificial scenario where we modify one parameter like preload but keep the other parameters like afterload, contractility, and compliance constant. Let's start by talking about what happens when there's an increase in preload. Shown on the screen are two pressure volume loops. The blue loop is the baseline state, the red loop is from a heart with increased preload. And this is very easy to understand if you remember what I told you before. The end diastolic volume, which is the volume at this point right here in the blue loop, that represents the preload. So if we increase preload, we simply move to a point a little bit further up the end diastolic pressure volume relationship, which is the black line right here. Therefore, this represents a higher end diastolic volume and a higher preload in the red loop. So I've summarized these points at the top of the screen. The end diastolic volume goes up when you increase preload. You'll note that the width of the red pressure volume loop is greater than the blue, therefore we've increased stroke volume. And then finally, we've slightly increased the ejection fraction by doing this. Why is that the case? Well, the stroke volume is the end diastolic volume minus the end systolic volume, and I told you that we raise the end diastolic volume when we increase the preload. This means that the ejection fraction, which is end diastolic volume minus end systolic volume over end diastolic volume, will go up slightly when we do this. And remember, this is very artificial. Normally when you do this, you would change contractility, but here we are keeping the afterload constant and the contractility constant just to show the isolated effects of an increase in preload. And if we decrease preload, we get the opposite of the changes we described on the last slide. The end diastolic volume falls, the stroke volume falls, and the ejection fraction falls slightly. If you look at the red pressure volume loop on the screen, you can see that its width is narrower than the blue one. That tells you that the stroke volume is lower. You can also see that the end diastolic volume is here for the blue loop and it's here for the red loop. that tells you that the end diastolic volume has fallen. If we increase afterload, we go from the baseline blue loop shown on the screen here to the red loop. I told you earlier that afterload is the point where the aortic valve opens. That's right here for the blue pressure volume loop. It's been raised to a higher point here in the red loop. The consequence of this is that when we eject blood in the red pressure volume loop, we hit this black line sooner. In other words, we hit it at a higher volume. So therefore, the end systolic volume shown right here is much higher than it is in the blue pressure volume loop. So the major consequence of raising the afterload is that it's harder for the ventricle to eject blood, so it ejects less blood. Therefore, at the end of systole, there's more blood left behind and the end systolic volume is higher. Because the end systolic volume is higher, the stroke volume is lower. You can see that the red pressure volume loop is narrower than the blue one. And when the stroke volume falls, the ejection fraction falls because stroke volume is the top term in the ejection fraction equation. Now let's talk about contractility changes. Contractility, it turns out, is the major determinant of the end systolic pressure-volume relationship. Those are the two lines shown in blue and red here. So when contractility decreases, it shifts the end systolic pressure-volume relationship from the dashed blue line to the dashed red line. That changes the pressure-volume loop from the blue loop to the red loop. So let's talk about the consequence of that. First of all, you can see that the end systolic volume here for the blue loop is much lower than the end systolic volume for the red loop. So in other words, the end systolic volume goes up significantly when there's a fall in contractility, and that should make sense to you. When there's less contractility, less blood is pushed out of the ventricle. Therefore, there is more left at the end of systole. Therefore, there is a rise in the end systolic volume when there's a fall in contractility. Because the end systolic volume goes up, the stroke volume goes down, and it's very easy to see that the red curve is narrower than the blue curve, and the fall in stroke volume makes the ejection fraction lower. An increase in contractility has the opposite effect. It moves the end systolic pressure-volume relationship to the left. That lowers the end systolic volume. More blood is being squeezed out with higher contractility, so the end systolic volume is lower. This leads to a rise in the stroke volume and a rise in the ejection fraction. Lastly, let's talk about compliance. Compliance, it turns out, is the major determinant of the end diastolic pressure-volume relationship. And it's very hard to talk about changes in compliance without also talking about changes in preload. One of the major determinants of preload is the compliance of the left ventricle. In order to fill the ventricle normally, you need a flexible, stretchy myocardium. If the myocardium is thick and stiff, then that will decrease the ability for the ventricle to fill, and that will lower the preload. So what I've shown on the screen here is what happens when there is decreased compliance, and this is the most important change in compliance that you should understand. When there's decreased compliance, the end diastolic pressure-volume relationship shifts up and to the left, as I've shown in going from the dashed blue line to the dashed red line. This has two important effects on the pressure-volume loop. First of all, the end diastolic volume, which is here in the blue curve, falls slightly to be here in the red curve. That's because the ventricle is stiff and it cannot fill as easily. In addition, the end diastolic pressure, which is here in the blue curve, is much higher in the red curve. That's because the ventricle is stiffer, so those molecules are packed into a stiffer chamber, and therefore the pressure in the ventricle at the end of diastole goes up. So I've highlighted these two important changes here that you should know. When compliance decreases, the end diastolic volume falls because of impaired ventricular filling, and the end diastolic pressure rises because of a stiffer ventricle. And if compliance were to increase, you would see the opposite of all these changes. Let me make a comment about the work of the heart. The area of a pressure-volume loop represents the work of the heart. The area represents how much volume it's pumping times how much pressure it's generating, and that determines how much work the heart is doing. So if you look at the two pressure-volume loops on the screen, you should be able to tell that the blue one is doing more work than the red one. The red one has much less area, and therefore that ventricle is doing less work. For the last few slides, I'll show you some commonly tested pressure-volume loops. These are loops that tend to come up on your exams. We'll go through all of these conditions shown on the screen here and talk about what they do to the pressure-volume loop. So the first one is aortic stenosis. Aortic stenosis raises the afterload, so therefore it moves us from the blue pressure-volume loop, whose afterload is right here, to a higher afterload in the red pressure-volume loop. Because afterload is higher, less blood can be ejected from the left ventricle, and therefore we have a lower stroke volume, and that is also what is seen in aortic stenosis. Mitral regurgitation shifts from the normal blue pressure-volume loop shown on the screen to the red one. It should be easy to note with your eye that this line here is crooked and slanted to the left compared to normal. The reason for that is because isovolumic contraction is disrupted. This line is supposed to be straight up and down, meaning that volume is constant. However, in mitral regurgitation, blood is leaking out of the ventricle into the atrium. Therefore, during isovolumic contraction, the volume is falling, which should not be happening. So it's very easy to identify the mitral regurgitation pressure volume loop because this line here is not straight. In contrast, in aortic regurgitation, the major finding in a PV loop is that isovolumic relaxation is disrupted. If you look on the screen here, the blue loop is a normal PV loop and isovolumic relaxation is a straight line. That means it's isovolumic. In the red loop, which represents a case of aortic regurgitation, isovolumic relaxation is no longer a straight line. It's curved. In other words, it's not isovolumic anymore. And the reason it is not isovolumic is because blood is filling the ventricle during relaxation, and that's because blood is leaking across the aortic valve and into the left ventricular chamber. And then finally, mitral stenosis produces the red pressure volume loop shown on the screen here. It's very similar to the blue one, it's just a little bit smaller, and that's because the ventricle can't fill properly. There's an obstruction to inflow from a stenotic mitral valve, so this slightly decreases the stroke volume and makes a pressure volume loop that is just slightly smaller compared to normal. And that concludes our video on pressure volume loops.